Ampere's law was a topic we covered a few chapters ago. And the idea of Ampere's law was that it was another way to determine the magnetic field from currents. So typically we use, for instance, Biot-Savart to understand the magnetic field from currents. Ampere's law is kind of like Gauss's law, in which you use symmetry to argue what the magnetic field is. So it only really works if you have a symmetric distribution, and it isn't something that you have to use in all situations. But to give a quick review of Ampere's law, the idea was that we had a surface. In this case, unlike Gauss's law, it wasn't an entire closed surface in terms of like a sphere. It would be a surface defined by a loop, and you would then have basically a two-dimensional surface. So this two-dimensional surface with this fixed edge, then you would take the integral, a line integral along the outside, so a path integral, of your magnetic field. So this works best when you have a symmetry like circles. And then that integral is equal to mu naught times the current through. So for instance, if you have two wires going through this surface, notice that one current goes this way, the other current comes this way. I through would be the sum of those, so it would be just the difference. But we didn't actually define the sign of this. So this worked okay for magnitude, but we didn't have any sort of definition for the sign. So Ampere's law is again something that we don't have to use in that many circumstances, but we have to understand it right now to understand where the displacement current comes from. So to understand the sign, what we can say is that if we have a surface S bounded by a closed curve C. So to go back up, we have a closed curve, which is kind of the black line here, and then the surface S, which is kind of this pinky color. You choose either the clockwise or counterclockwise direction around C. And the reason you would need to do that is because you're doing a surface integral. So notice that here, if you just look at the way the magnetic field is pointing, it looks like we would be doing this counterclockwise. Then you curl your fingers of your right hand. So anytime you see this, that should tell you the right hand rule. And you're going to curl your fingers in the chosen direction. The thumb is perpendicular to the surface. Your thumb then defines the positive direction. So this isn't too hard then, and what this allows you to do is define the flux, which we can think about as, for instance, current through, as positive or negative. So if we've talked about flux before, and here we're talking about the current through the surface. So in the direction of your thumb, it's positive, and flux, we usually talked about fields. So here we're basically just saying if I have some sort of loop and I have some sort of surface then that is inside the loop, you pick a direction, say this one, and then using the right hand rule, you figure out which way is positive, which way is negative, and based on this way, this is then the positive direction. So this isn't that hard. So something that we didn't really talk about before when we learned about Ampere's law was thinking about how we define the surface. So again, remember that we have a closed loop, C, and we have our surface. So our loop in this case is here. Now typically what we do is just think about the surface as being kind of like the flat surface defined by that loop. But that doesn't have to be the case. What we can do is actually use this surface. So imagine basically blowing a bubble, right? So if this was a layer of gum, we can blow it into this bubble. Now notice that this black line out here isn't our curve, that's just the edge of the surface. So one closed curve has more than one possible surface that is defined by it. We have surface 1 and surface 2. Notice that if we have a wire here carrying current I, it's going to go through both of these, right? Because if this wire suddenly ended here, there couldn't actually be a current going through it. We can imagine another scenario where the wire goes and turns around. Now in this case, no current goes through surface 2. But if you look at surface 1, you have a current in and a current out. Remember that current is always conserved, so I in equals I out. So in both of these cases, I total equals 0. So we call this I through. So this argument is basically that we can use any surface we want as long as the edge of that surface is defined by this curve, right? Again, you can imagine this as blowing a bubble outwards. We could make it do something more complicated if we wanted, but mathematically, these should be identical. And again, we could make the surface further and further out. We could, make it kind of funny shaped, as long as there are no holes in it other than no holes in it, and the only edge is given by this curve. So that's the idea of Ampere's law. Now, the reason we're talking about this is because we're going to have a problem. Imagine now that we apply Ampere's law to a charging capacitor. So now this is effectively a side view. Remember that we've had this surface, the curve, and we've had the surface, and that's actually what you're seeing here. So the black line, you have basically a side view. So that black line, you just see a dot, and your curved surface there is that. So we said that we could kind of blow this outwards and have it be this curvy surface, which is then this one. So that's what we're doing here. But now notice that we do have a current passing through this surface, right? There's a current here. And so this works. I through is equal to I. But once we take it out here, it looks like there's no current passing through the surface. But it's defined, these two surfaces, by the same close curve, which again we're seeing as an edge-on view. So this is a problem with Ampere's law. Again, mathematically, these two surfaces should give us the exact same current through, because when we integrate the magnetic field over this loop, we get the same value. So displacement current is an idea introduced to actually fix this problem, and the next video will go through that.